So now that we know how d orbitals split in energy upon entering a ligand field for a transition metal complex, let's talk about what happens to the electrons on the metal. So this is the d count that we were so focusing on for the past couple weeks. So suppose we have an octahedral complex, so again Ml6, and so we know that our d orbitals split like so. Again, T2G, Eg. So as we start filling in electrons, electrons, of course, fill in according to the same rules that we talked about before, Hund's rules, et cetera, et cetera. So as from D0 through D3, they fill in kind of as expected. So we have just 3 electrons. So if we end up having more than 3 electrons, then we might have a choice. So let's say D4 through D7. Through D7. So we fill in for our first 3 electrons. I'll just draw. There's two choices. So our 4th electron could go up here, or it could go over here. So the same thing could happen with 7. So you can figure it out. So this is, we could have 1, 2, 3, 4, 5, and then 6, 7. I guess I'll do that as well. So 1, 2, 3, 4, 5, 6, 7. So we fill in the 5 electrons first before we enter the T2G. Or we could fill in all 6 here and then go 7 here. So these 2 scenarios are called high spin, and low spin. Alternatively, you might also see them called weak field, and this is also strong field, for reasons I'll get into. So what dictates whether this happens has to do with our delta O. So keep in mind again, so remember this is delta O. But also, as if we start putting 2 electrons in the same orbital, we have pairing energy. So those are our 2 competing energetic factors. So pairing energy I'll call P, but you might also see it called pi in some textbooks. So basically, we fill in our first 3 electrons, D0 through D1 through D3, and then our 4th electron, we have the choice whether we want to go up. So to put the electron in the EG set will cost us delta O in energy, but to pair the electron instead in the low spin scenario, that will cost pairing energy because there's electron-electron repulsion. So typically, what governs whether we go high spin or low spin depends on delta O versus P. So if your delta O is delta O small, right? So if our energy gap between our EG and T2G manifolds is very small, it's easier for the electron to go into the EG than it is to pair, right? So then you want to go delta O small, we'll go high spin. Delta O big, P small, then we'll go low spin. So delta O is, the factors that govern delta O are your metal ligands. Pairing energy is usually based on, typically your metal. So if we want to predict whether something will go high spin or low spin, well, some rules of thumb. What we know is that, let's see, so the pairing energy for 4D or 5D elements is much, much less than the pairing energy for 3D. And that's because, as we know, 4D and 5D orbitals are much larger than 3D orbitals. So therefore, it's easier to fit 2 electrons in them. That's kind of simple. Also, we talked earlier about the kind of the d orbital, how much they extend out. So the d orbitals extend for the 4D and 5D extend out further than the 3D. So the 3D kind of is shielded, blocked by that 4s orbital. So as a result, 4D, 5D elements have stronger bonding to their ligands. And then as a result, because of stronger bonding, we have bigger delta O. So delta O for 4D, 5D is also greater than delta O for 3D. So taken together, as a result, 4D, 5D complexes are low spin. And then 3D can be either low spin or high spin. So this is dependent, whether the 3D complex is low spin or high spin depends on the metal, its oxidation state, also the ligands, which we'll talk about in our next class. So yes, these are kind of the common factors. So we want to know high spin versus low spin. So there is the choice, and that, of course, what happens to it changes its final properties. Like it'll change the color, it'll change its reactivity, et cetera, et cetera.